I am delighted to prove that E is irrational. This is going to be a lot of fun because it uses proof by contradiction, which is a technique we are learning in math reasoning, and it also uses Maclaurin, polynomial, and remainder, which is from Calculus 2. So it's a very nice merge of ideas from the two subjects. I am going to use the definition of E, or I should say this is how I'm defining E, that you take this infinite sum 1 over k factorial as k goes from 0 to infinity. And if you think about this, why can I do this? Just to remind you, and I will be using this in a little while. If we write down the Maclaurin series for e to the x, we have x to the k over k factorial, and we sum k equals 0 to infinity. This was the Maclaurin series, and this converges for all x and equals the function e to the x. So this is something that we are using, and in particular for x equals 1, you see you get exactly this expression for E, which I will use as the definition. The first step is we must show that E is between 2 and 3. Now, as I mentioned, I am not using a calculator here. I am going to use this as the definition of the number E. So I won't type it into a calculator to realize this. I'm using this only. Okay, well, to see that E is greater than 2, this is the easier one to realize, because if you look at these terms, well, this is one positive, 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 positive. So this is strictly bigger than the first two terms, which add to 2. Okay, very nice. On the other hand, bigger than 2. So also, if I write this, I want to say this is less than something. And perhaps I will, okay, I'll leave it like this. But I will come to the side and do a little bit of work. So this is a little side work box. Right now I am only trying to show that E is less than 3. Okay, if I look at 2 factorial, this is 2 times 1, this is 2. So 1 over 2 factorial is a half. Okay, that was, I didn't even need a side work box for this, but in any case, let's continue. 3 factorial, 3 times 2, well, this is, this is strictly bigger than 2 times 2, which is 2 squared. And 4 factorial is strictly bigger than, if I have 1, 2, 3 2's, 2 cubed. And similarly, I could continue. 5 factorial is strictly bigger than if I had 1, 2, 3, 4 2's, because you see, if I did 2 times 2 times 2 times 2, well, it's definitely less than this, because 5 is bigger than 2, 4 is bigger than 2, 3 is bigger than 2, and then we have a 2. So this is strictly bigger than 2 to the 4th. And this would continue. Now, what does that mean for the fraction? Well, when I take 1 over, it switches the inequality. So here, 1 over 2 squared is greater than 1 over 3 factorial. 1 over 2 to the 3 is greater than 1 over 4 factorial. 1 over 2 to the 4th is greater than 1 over 5 factorial, like this. So I can say that this is strictly less than, I'm going to have 1. Well, the 1 plus 1, maybe I'll just add. 1 plus 1 is 2. And then I have plus, I am the 1/2. Okay, but then here's where the strictly less than comes. And the next term would be 2 to the 4th, things like this, okay? I'm doing this to figure out, well, I would hope this whole thing is less than or equal to 1, and then I will get that e is strictly less than 3. We're going to see this now, because if you look at this part, and this is the beautiful thing about series, is being able to use it something like this. What do you see here? Well, this is a geometric series. This part is geometric. My initial term is 1/2. And my ratio is 1/2. And anytime the absolute value of the ratio is strictly less than 1, so absolute value of r less than 1, we know that this converges, and it converges to a over 1 minus r. And so if I continue here, this equals 2 plus a over 1 minus r, and this is 1/2 over 1/2, which is 1, which is 3. Okay. Now, what we see here, okay, maybe it's time to erase my side work box to make a conclusion, because I have this line, explanation, this line. Now let me erase. We can just say, thus, we see that e is strictly less than 3. And step 1 is complete. So we have shown that 2 is less than e is less than 3. This is step 2. It's our last step before we begin the proof. And this is to find an upper bound for the error when approximating e by or with the nth order Maclaurin polynomial for e to the x. And this is the Taylor polynomial with center 0. So let me remind you, this calculation is completely Calc 2 material, but let me remind you what we know. We know that e to the x is equal to the nth order Taylor polynomial at 0, or Maclaurin polynomial, plus the remainder. Okay, and then what else do we know? Oh, well, I'm going to try and get a bound on this, and usually we have some interval. In fact, we need one here. I'm approximating e, which is e to the 1. My center is 0, so we will use the interval 0 to 1. Now, what can we say about the remainder? We know the error, which is the absolute value of the remainder, equals the remainder itself, this is Taylor-Lagrange theorem, is equal to the n plus first derivative at c over n plus 1 factorial times x to the n plus 1. To get the error, I put everything in absolute values. This remainder equals this for some c between 0 and 1. For some c, I will write it this way. And I can certainly put the closed interval. It's still a true statement. Now, we don't actually ever find c, if you remember this from class. But theoretically, we know that it exists. So we're going to use this to find a bound on this error. Well, if you think about this, what is the n plus first derivative of e to the x? Well, it's e to the x. E to the x has the same derivative for all And you just keep differentiating e to the x like this. So this is equal to e to the c, which is positive. So I don't need my absolute values on this part. This is positive, and then I'm only looking between 0 and 1, and so this is non-negative. Okay. Now we have to think about bounding this. Well, we have these two different things. We have e to the c, and we have x to the n plus 1, and we need to see how big can each of them be on this interval. This part, e to the c, is an increase, or e to the x, I should say, is increasing. So here, this part increasing. Because it's increasing, the largest it will be is on the right endpoint. So this will be less than or equal to, this will be e to the 1 over, and then I'll leave this alone. I usually do this in 2 steps to get my bound. First, I bound the derivative, and then I will bound the power of x. Okay? Now, maybe I'll work with this, the x to the n plus 1. The biggest this can be between 0 and 1 is at 1 to the n plus 1, which is just 1. So this is less than or equal to e over n plus 1 factorial. The final thing I will do to bound this error, or bound the remainder, is here. We have shown e is strictly less than 3. So this is less than 3 over n plus 1 factorial. And so this term here, this is what we have found, that the error, in this case, the remainder is positive anyways on this interval, but that it is strictly less than 3 over n plus 1 factorial. Are you having fun yet? I hope so. The last thing to do is our proof by contradiction. We have built everything we need. We have shown e is strictly between 2 and 3, and we have shown I'm really only going to need the remainder at this one value, x equals 1, but the nth order Maclaurin remainder is strictly less than 3 over n plus 1 factorial. Okay, now we are ready to begin our proof by contradiction. Here we go. By contradiction. Let's assume, well, in a proof by contradiction, you always assume the opposite of what you're trying to prove. Then you make arguments until you reach something that's always false. This is a contradiction. If you conclude something that's always false, your original assumption must be false, or equivalently, what you're trying to prove is true. And we have discussed this in math reasoning. So proof by contradiction, we assume this statement is false, namely that e is rational. So we assume there exists, we need 2 integers, and we will have b not equal to 0. E is of the form a over b. This is the definition of a rational number. This is our assumption. We assume it is rational. We will reach a contradiction, and then therefore we have proved it's actually irrational. Well, I'm going to use this here already. Because e is strictly between 2 and 3, e is not an integer. And e is positive. So in particular, as 2 less than e less than 3, we can have both of these positive, but I will say that b is going to be greater than or equal to 2. Because if it was 1, e would be an integer, right? So b is greater than or equal to 2. So now what we want to do is we want to consider the bth order Maclaurin polynomial, poly with an n, nomial for f of x is e to the x. Okay, so I will write it over here, perhaps in blue. Let's draw a little line. We will write it here. The bth order, well, the notation here is T, B, F, X, 0. And this is 1 plus x squared over 2 factorial, all the way out to x squared, to the b over b factorial. And perhaps I should extend my box. Okay, that is what we have shown. Okay, well, this is the bth order Maclaurin polynomial. And then we know, for example, that e to the x is equal to this plus the remainder. Okay, now let's go back, and maybe I will switch back to black. Let's go back to x equals 1. We have, well, that e is equal to 1 plus 1 plus 1 over 2 factorial out to 1 over b factorial. There's a plus here. And then plus this remainder at 1, okay? Or using this here, e is a over b, we really have that this sum here is equal to, maybe I will just change it, a over b. Okay, so I've used this here, that e is equal to a over b. This is really what I need to express it because I have b's on both sides of the equation. So now let's multiply both sides of the equation by b factorial. And we get b factorial times a over b equals b factorial times this. Maybe I'll put this term, 1 over 2 factorial, out to 1 over b factorial. And then it's a b factorial times r to the b f of 1, 0. Then we need to make an observation. And this is quite an important one. First of all, this here, we see this is b minus 1 times factorial times a. That's the left-hand side. But something similar happens when you distribute. So the first term here, it's b factorial plus b factorial. When you get to the next term, it's b factorial over 2 factorial. But this is an integer, right? If you think about, maybe I will write it underneath and then erase. If you think about b times b minus 1, b minus 2, out to 3 times 2 times 1, and then over 2 times 1. The 2 times 1s, you see, will cancel. So this and this cancels, and you just get this product down to 3. Of course, unless b is 2, in which case we have a 1 here, still an integer. Okay? So this is an integer. We would continue to the next one, integer for this similar reason, all the way down to b factorial over b factorial. And again, this is an integer. B factorial over b factorial is 1. Okay. And then this final term in this sum is b factorial r to the b f1, 0. Okay. Now this looks like it's going to be complicated, but we're actually in really good shape because this thing, whatever it is, integer. This thing, integer, okay? So we may write, so then b factorial times this remainder this must be an integer because it's one integer minus another. The difference of two integers, right? This is an integer. This big expression is an integer. You take one minus the other, we have this. However, look here, we use this bound that we have before. So however, we know it's positive. We discussed that in the last thing. Maybe I could have added a greater than 0 on the other side. But this, I'll put it here. And this is strictly less than 3. This is going to be b factorial over b plus 1 factorial. Now you have to think about this, right? Because we can cancel some things here. This is equal to b plus 1 factorial is b plus 1 times b factorial. So this is 3 over b plus 1. This is where wonderful things happen because remember, b is at least 2. So b plus 1 is at least 3. So this is, I'll do one more, less than or equal to 1. We have 0 less than this number, b factorial times the remainder, strictly less than 1, okay? So as 0 is less than b factorial times the remainder, strictly less than 1, okay? We have, well, it cannot be an integer. So b factorial times the remainder is not an integer. And this is our contradiction because look, we have b factorial times the remainder is an integer. We have b factorial times the remainder is not an integer. We have a contradiction. Therefore, this assumption here that e is a over b, this is not true, showing that e must be irrational. Okay, this is our proof by contradiction.